The first thing you need to know is, what is blackbody radiation, and why is there such a fuss about it? So let's get started. Here's a red clay pot. It gets the red color from reflecting some of the room light. Light is electromagnetic radiation that your eyes can detect. There's a much larger range of electromagnetic radiation that your eyes can't detect. Physicists call the whole range radiation, and the word light is usually reserved for the small part of the range that you can see with your eyes. Under ordinary conditions, the color of an object is partly determined by the material it is made of. Another type of clay may look blue or yellow. We are so used to this situation that we say that the clay itself is red, when what we mean is that the clay preferentially reflects red light when exposed to white light. If you change the color of the room light, then the observed light from the object also changes. Thus, the white fabric under this pot looks red when a red laser is shined on it. Another common experience is the light from an enclosed space. I will enclose some space by placing a clay saucer on the pot. Now I presume that the space inside the pot is dark. We can verify that presumption by looking in a little hole through the walls. There happens to be one in this clay pot. And you see that the inside is black. It will be black whether you start with red clay, green clay, or blue clay. It's a reproducible phenomenon that doesn't depend on the material or the room light. So far, your reaction should be boredom. Now, in the early 1800s, the Industrial Revolution was starting, and the steam engine was extremely important. Many laboratories were working on ways to make steam engines more efficient, and that meant they had ovens where they could raise temperature in a controlled manner. As they raised the temperature of enclosed spaces to about 2200 degrees, a reddish glow began to emerge. I can simulate that with video effects. They tried various types of containers and found that the color of the glow was the same no matter what the container was made of. Red clay, blue clay, yellow clay, all glow the same. They tried various sizes of containers and found the glow doesn't change with the size or shape of the enclosed space. A small bean-sized space will glow the same as a basketball-sized space. The color profile of the glow only depends on the temperature of the container walls. At 2200 degrees it is red, and by 3000 degrees it's almost white. Now your reaction should be one step above boredom. Here's a phenomenon that doesn't change under a wide variety of conditions and can be reproduced in any laboratory. This sort of thing allows science to progress. Even though the enclosed containers glow red through blue, the name blackbody radiation stuck. At room temperature, the radiation is mostly at infrared frequencies, which humans can't see. We call it black. Normally, we don't see objects at 2000 degrees, where they start to look red. Charcoal in a fire glows red, and this has some of the characteristics of blackbody radiation. But the charcoal is not in thermal equilibrium with its surroundings, like the interior of a heated vessel. The sun is often approximated as a black body at 5700 degrees, but there again, it's not truly in thermal equilibrium with its environment. Incandescent light bulbs are also approximated as black bodies at about 3000 degrees. That's enough of the real-world stuff. Let's get back to the laboratory. Simple measurements of blackbody radiation were first made around 1850. By 1880, experimentalists had figured out how to make full spectral measurements at a variety of temperatures. They plotted their data with frequency on the x-axis and response of their radiation detectors on the y-axis. At room temperature of 300 degrees Kelvin, the detector has no response and the curve looks like this. As they increase the temperature, the detectors began to sense a little bit of infrared radiation. We can't see it, but we can feel it as heat. Heating further to about 2200 degrees, they started to see a red glow coming from the hole. Some of the blackbody radiation was moving into the visible region. Raising the temperature further caused the total amount of radiation to grow dramatically, and more moved into the visible region. At 3000 degrees, the glow was yellowish-white. At all temperatures, the curve moved up to a maximum and then trailed off to zero at high frequencies. The frequency and height of the maximum depended only on the temperature. By 1890, experimental physicists had collected a large set of data. The stage was set for theoretical physicists to explain the curves. Physicists began by using the tools they had: Newtonian mechanics, statistical mechanics, and Maxwell's theory of electromagnetism. They found that these tools could explain the observed behavior at low frequencies, but could not explain why the curve came back to zero at high frequencies. That was bad. Classical physics was predicting that the radiation energy in an enclosed vessel was infinite. Said in practical terms, classical physics could not allow you to bake bread. You would never have enough energy to heat the oven. In 1900, Max Planck proposed a resolution to the paradox with his quantum hypothesis. It was revolutionary back then, but now it's one of the foundations of physics and modern living. In the next video, we begin the story with a review of classical mechanics.